Good afternoon. This is David Eastwood, Geotech Engineering and Testing. How you doing today? Today we're going to be talking about geotechnical considerations in design and construction of subdivision streets. Um, During the past few years, I deal with a lot of clients, a lot of production builders and residential developers, civil engineers. A lot of them complain about some of the counties around Houston um, that they require 7-inch or 8-inch concrete paving for their subdivisions. And when we talk to some of these counties, they really don't have any good reason for going with, with 7-inch or 8-inch concrete paving. I had a meeting with a developer the other day. He said that he's got a project development in Grimes County, and they require 8-inch concrete. That's going to cost him $5 million more in construction, going to 8-inch concrete as opposed to typical 6-inch concrete, which is performing just fine everywhere in Harris County and Fort Wayne County, Galveston County. And so, um, I'm on the board of director of GHBA Developer Council. So I put this presentation together to address some of these comments and basically approach it from an engineering standpoint, talking about the soils that we have in Texas, and go through the pavement design using AASHTO pavement design, showing that for subdivision streets, considering the traffic loading that's out there, all you need is 6-inch concrete paving. So with that, I'm going to walk you through basically what we do when we get involved in soil testing for a subdivision street. How do we test the soil, and what do we go through the engineering design using AASHTO, and of course, how you construct it and how you stabilize that subgrade, because the subgrade construction is very important. All this design that we have in here assumes that we stabilize that subgrade at least to a depth of 8 inches. So with that, I'm going through this. Audience, we have developers, home builders, and a lot of civil engineers, with people from the cities and counties. We got about 134 people RSVP'd. So that's what we got. Here's my contact information. Um, my email is de@geotecheng.com, and my phone number is 713-699-4000. This is going to be on YouTube. We got a YouTube channel where we got a lot of presentations. You can go watch it, use it for training of your staff. And once they watch it, they can send us an email and we'll send them a PDH information. Geotech Engineering and Testing is located in Houston. We work all over Texas, Louisiana, New Mexico, Oklahoma, Arizona. We've been around about 40 years. We do geotechnical, environmental material testing, and geoforensics. We have about 60, 65 people. We got our own rigs, full laboratories, so we're pretty quick on our projects. If you have any questions, you can put it in the chat section or Q&A. I check it and try to answer it as we go through. So what we're talking about is subdivision streets, and these are usually low traffic, roads, and they're typically in most counties that are about 6 inches thick, and they should come in all shapes and forms and locations. And first thing we do, of course, when we get involved in a study for a subdivision street, we go out there and get soil samples. These are our rigs here. Some of our rigs, not all of them are here. Some of these rigs go pretty deep. These portable rigs go 20 feet. These other rigs go 35. These big guys go about 120 feet deep. So if you got a bridge on your project or a lift station, we're going to use the big rigs. If your site looks like this is the typical truck mounted rig we use for like roadway. The borings for the roadways are about 10 foot deep. If your site is wet and you can't drive on it, you got to use our buggy rig. We got buggy rigs. We get out there and try to get the borings done. He's got big tire. It just kind of costs more money. These are just a subdivision out here we did for one of the production builders out there in Fort Wayne County. If your site is wooded, of course, we clear a path with a dozer and get out there, do the borings. Sometimes we use our portable rig system, pull it behind one of our ATVs and get out there, do the borings. Goes about 20 feet deep on these portable rigs. That helps out considering all the rain we have had lately. We can get out there and get the job done even if the site is wet with our portable rig and keep it economical. Most of our sampling is done, of course, with a Shelby tube sampler. These are 3-inch diameter steel tubes that hydraulically push them into the soil. That's what you get in the soil samples. It's the old fat clays, Fort Wayne County, for example. You cut the ends of it, put it in foil, give it a job number, boring number. You put it in a wax box and plastic. We try to test it in 14 days. Otherwise, you lose the moisture and the soil gets hard, and so you don't get proper test results. If your soils are sandy, we test it with a standard penetration test. That's called SPT, and that's a 140-pound hammer that drops 30 inches. This SPT hammer, you drive into the ground 6 inch, 18 inches into the ground to get a sample of the soil. It's a split spoon sampler. What it looks like. If your soils are 0 to 4 blow counts, it's very loose. 5 to 10 is loose. Medium dense, 11 to 30. Dense, 31 to 50. So if I'm doing a roadway, a lot of times my soils are very loose. If they're sand, or too loose, you go out there in bridgeland places like the Woodlands or Katy or 249 and 290 corridors. You go to some of these counties like Waller County, that got a lot of sandy soils and they're very loose on the surface. If you go deeper, you're going to hit rock. Rock in Houston is about, 2,500 feet deep. But if you go in San Antonio, Dallas, and Austin, especially San Antonio and Austin, you're going to see some rock sticking out of the ground. So if you put a street on top of it, that's great because you got a great subgrade. So the stuff I'm talking about today is on soil, clays, sands, and silts, which are a lot weaker than rock. So a 6-inch paving on a rock will perform much better than, of course, a 6-inch concrete paving on soil. So a lot of the stuff that I'm talking about is applicable everywhere in Texas. Groundwater, typical groundwater, like in Houston, could be about 15, 20 feet or 30 feet deep. You get a tape measure with a weight at the end of it. You drop into the hole. You hit the groundwater. Sometimes we're running two perch water tables. So if you go to Katy area, for example, you got the sand layer over a clay. Water just sits on top of the clay. It cannot penetrate into the clay. And just sits right on the top. Called perch water table. Regular groundwater table could be 20 feet deep, but perch water table is about 5 foot deep. So if you go out there in south of Conroe, for example, south of 336, you got lots of perch water table. Geotechnical guidelines for pavement design. We use geotechnical guidelines, Chapter 11, City Houston or Harris County geotechnical guidelines. You do one boring every 500 feet spacing to a depth of 10 feet. Lab testing, these are some of the basic lab tests that you got to know when you do soil testing for pavements, foundations, or whatever. You do liquid limit tests. This test, you add water to the soil in here. When it becomes liquid, you put it in this cup in here. You cut a groove through it, cut the with this spatula, and then turn the handle and 20 to 30 times. And when the groove comes together, you get a sample of that soil. You put it in, on the scale and get the wet weight of it. And you dry it up in the oven. And once you get the dry weight of it, and then you know how much water is in the soil for it to behave liquid. The other test we do in the lab called plastic limit test. At this test, what we try to figure out is how much water we should add to the soil to behave semi-plastic. And we got to roll up the soil in 1/8 of an inch in diameter and get the wet weight of the soil. And you put it in the oven and dry it up and get the dry weight of the soil. So we get the moisture content by subtracting the wet from dry, and we know how much water in the soil is when it behaves semi-plastic. The difference between liquid and plastic limit is plasticity index, or PI. So you got PI less than 20, you got low swell potential. Is 20 and 30 is moderately expansive, 30 to 40 is highly expansive, above 40 is very high. A couple other tests we do in pavement design is a hand penetrometer test, torr vein test. In the hand penetrometer, we get that soil and push this thing into it. You can read here what kind of a strength you have. Torr vein, you put it at the end of the sample, assure the torsion. You can read what kind of a strength you have here. Unconfined compression, you got the loading ring and the deflection dial gauge, and you shear the soil, you put load on it, and you want to know how much load you can put that soil, so how much load you can carry. That goes into your pavement design, your design of your foundations, it goes into your trench safety, all that kind of stuff you use for. Gradation, if you got soils like sandy soils or clay, you run gradation tests on it to see if it is sand, clay, or is it rock? Is it, what is it? You do gradation on it and run it through the sieves and you shake it. You get a, curve like this. This is sieve test results. And, for example, this one here, passing number 200 to 66%. That's the sandy lean clay soil. This one here, you see the gradation here, number 200, and you can see percent passings, but less than 20%. So it's mostly coarse aggregate. Particle size for gravel, you got to be less than 3 inches. Sand got to be less than 0.187 inches, and of course, silt and clay got to be less than 0.0029 inches in size. Compaction, the soils underneath the paving got to be compacted. You run a Proctor test. This is natural soil. You get a fat clay that you may run into in North Conroe or Fort Wayne County or Brazoria County, these fat clays. This is your select fill. And you get a bucket of that fat clay, a bucket of your select fill. If you need fill for your mass grading or so, you go to a pit and you dig the pit is a big hole in the ground. It's got different soils in it. Some people say, well, the soil is the same in a pit. That's not correct. The soils are variable in a pit. So you got to test the soil as it's coming out. This is sandy, this is clayey soils. You get the sample of the clayey soils. You don't want to use sand. You put it in, this is a good sandy clay, structural fill. Put it in the back of the truck, put it in a hopper, and take it to the job site. This is your fat clay. You bring it to the lab, you spread it out, you dry it, cut it to pieces, small, add water to it, and you compact it. This is a 4-inch mold. It's a 5.5 pound hammer, drop 12 inches, 3 layers of the soil called standard Proctor test. It's 5.5 pound hammer, 12 inches drop, 25 blows per lift, 3 lifts. You compact it in a machine. And of course, the weight of this thing and the volume. That's a sample of the soil compacted. You weigh it, you know the volume, you get a Proctor curve. So all your soils, that's again, when you do these pavements for these subdivisions, that soil should be compact 95% of standard Proctor density. And this is what the Proctor is. Again, in our pavement design, we assume a strong subgrade. We assume you get these soils, you stabilize it with lime or lime flash or cement. So that's very crucial where you get a good Proctor on it. That's the optimal moisture. This is maximum dry density here. You want to compact 95%, which is 115 pounds per cubic foot at moisture content plus or minus 2%. Goes all the way from 9 to 13%. So when you compact the soils, this is the Proctor curve, and this is the strength curve. And you'll find out at the optimal moisture, you develop the maximum strength. So it's important to compact the soil near optimum to develop the maximum strength on the soil. One of the other items that is important in pavement design using AASHTO is CBR, California bearing ratio. Again, this is getting a little technical for the developers. You know, you kind of be patient. Because there are a lot of engineers here, so I got to talk about some engineering in here. CBR is defined as the ratio of compacting the barrier of a material with bearing of a well-graded crushed limestone. Basically a ratio of their strength. So if you got a natural clay, you compact the strength of it. You compare that to a crushed limestone, well-graded crushed stone, and of course, you know the clay is much weaker. And we tested. You measure the load at 0.1 inch and 0.2 inches. For crushed stone is 3,000 pounds to have a penetration of 0.1 inch. For crushed stone at 0.2 inches, it requires 4,500 pounds loading. So you basically got a piston on 1.95 inches. CBR for crushed stone is 100. And of course, you soak your sample for 4 days with 1 psi paving load to model what happens to your road that sits out there in the rain, and that we have a lot of rain here. And of course, one of the parameters that you need in your pavement design is resilient modulus, which is 1,500 times CBR. So basically, you got a 5.5 pound hammer, drop 12 inches, or you use modified, which is 10 pounds, and drop 18 inches, depending on the compaction requirements. And you compact it at 56 blows, 25 blows, and 10 blows per layer. That's the hammer. You know, you go out there and compact that soils with it. That's the mold is about 6 inches. You put it in the water for 4 days to model what happens when the soil gets saturated. You put it in a machine. This is a 1.95 inch piston, and you load it up. That's your 1 psi load to model the load of the pavement. That's the penetration. So that's for the soil that's compacted and stabilized. So you go out there and see what you put in the machine, and you see at 0.1 inch, you got a load of about roughly about 142 pounds. At 0.2 inch, you got load of about 183 pounds. When you calculate the CBR at 0.1 inch, use 414.2 at 0.2. At 0.2 inch is 12.2. So for design purposes, you would use a CBR of 12, the lower value. Engineering analysis, the type of soils we have in Texas, you know, you go to Harris County and Fort Bend County and Brazoria County, and north of Conroe, we got these fat clays. You know, there's a fat clay site. You go out there in Waller County and go parts of the Harris County on the west side and part of Fort Bend County. You have these sandy soils, and this is a sandy site. You got silty soils that you see out there in the Woodlands area, the Bridgeland area. 249. The grain size of the silt is bigger than clay, but smaller than sand. That's the silty soils, really hard to material to build a road on top of. You got to stabilize it, make sure you got good drainage. So we got clay soils, you go deeper, you get orange clay, you go deeper, you get white clay, you go deeper, you get into weathered rock. That's rock below that. Fill, a lot of projects when you do mass grading, you want to put a residential street. You're going to have a bunch of fill, depending on the site. You may have 3, 4, 5 foot of fill on your project. You can build your road on top of fill, provided it's properly compacted. You got to run density tests on your roadway at 50-foot spacing. You know, every lift, every 8 inches got to be tested. You have to have density test results. And of course, top 8 inches got to be stabilized. And if your soils is fat clay, you stabilize with lime. If it's sandy or silty, you stabilize with lime fly ash or cement. So if you go around Houston, you go out there in Montgomery County, south of the, Conroe, you will have sandy soils. You go north of Conroe near Chambers Creek, you got really fat clays. You go to Kingwood near 59, you got fat clays. You go near Cosby and Bellevue, Baytown, LaPorte, Seabrook, Leak City, on Friendswood, Pearland, Missouri City, Sugarland, Rosenberg, Richmond. All these guys got really fat clays. You got the Fulshire. Parts of it is going to be fat clays. Some areas going to be sandy. Katy area, you got real sandy soils. Brookshire, Sealy, you got sandy soils. Bridgeland, we got sandy soils out there. Farfield, sandy soils. Tomball, you got some areas that are fat clay, some of you are sandy. Magnolia, mostly sandy clay and sandy soils. And of course, you go out there inside Houston, you go Westview, Bel Air, Tanglewood, lots of fat clays and these oak trees. And so you got different types of soils around Houston. Of course, it goes with everywhere around Texas. You're gonna have different type of soils. You go around Texas, you will see fat clays in these areas of Texas and Louisiana. Texas soils are variable, so you got to know what kind of a soils you have. Again, if you have rock, you got the best subgrade. So your 6-inch paving would perform very good on top of a rock. These are the soils that may expand up to 1,500% in the U.S. So we have a lot of fat clays around the U.S. It's by Corps of Engineers. So when they did the land plan for Texas, they put Dallas, San Antonio, and Austin in areas where we got a lot of fat clays and gumbo clays, and El Paso, Lubbock, they got a lot of sandy soils and caliche type stuff. Again, you got the fat clays you can see. So when we do a roadway job, we do borings for a depth of 10 feet. You got fat clay here, got a PI of 38. Soils are strengths here are pretty good, 1,000 PSF. You can carry the paving load. And of course here, we didn't hit any water. There was no water. Here's the other side, sandy, silty soils, and 32% passes number 200 sieve. So that's, you got to be line fly stabilized. It's going to pump. We've got a perch water table here. So depending on the county, like Harris County, you got both clay and sandy soils. Fort Bend, majority, you got fat clays, gumbo clays. Some areas you got sandy. Montgomery County, you go south of Conroe, you got sandy soils. North of Conroe, you got fat clay. Brazoria County, for most part, unless you're near the beach, you got fat clays. Galveston County, you got some areas got fat clays out there near Leak City and Texas City. Um, you got fat clays. You go to Galveston, you got sandy soils. Liberty County, for the most part, you got fat clays, gumbo clays. Waller County, most of it is sandy soils. Most of it is sandy soils in Waller County. Chambers County, you got some areas that got clay soils, some areas got sandy soils. Same with Walker County. Grimes County has got some areas got fat clay, some areas got sandy soils. So just these are just kind of the counties that we see a lot of activity at. and they're going to have different types of soils, but everything we're talking about here is applicable to these type of soils. Concrete pavement design, for these subdivisions, streets, we use ISO pavement design. Again, engineers, that's your paving load. You're going to go through the pavement section. You want to keep the stresses minimum to the subgrade. So what you do, you put the concrete paving here, of course, and below that, of course, is stabilized layer. We use ISO 1993 pavement design. Um, we look at traffic loading, how much trucks and cars that goes on your subdivision streets. These things are so light that they don't really affect the life expectancy of your pavements. We calculate the traffic loading on the basis of equivalent single axle load defined by ISO. Traffic loading for, of course, major thoroughfare is about 10 million. That's not the kind of the loading that we use for, of course, a subdivision of streets. So the type of paving for subdivision street that we use based on ASHTO 19, if you have a high traffic area, your ESL loading is 700 to 1,000, uh, 700,000 to a million equivalent single axle loading for high traffic. For medium loading is 400,000 to 600,000 ESAL. For low traffic loading is 50 to 300,000, from 50,000 to 300,000 ESAL. Now, kind of like for your understanding of that is for high traffic loading, you're gonna have 107 1,750 million individual cars on it for a typical life expectancy of the pavements. Can you imagine the number so big? Or you can have 700 million trucks during the life of the uh, uh, pavements. Or combined is, 1 billion, 1,000 million uh, trucks and cars combined, 50-50%. For medium traffic loading, you could have 400 to 600,000 ESAL, and you can have anywhere cars of 1 billion to 1.5 billion cars go on it. And trucks, 400 million to 600 million, and combined 571 to 875 million vehicles go over your pavements for the life expectancy of it. For low traffic loading, 50,000 to 300,000 ESAL, you can have 125 million cars to 750 million cars for low traffic. And you can have 50 million trucks to 300 million trucks. Combined 71 to 428 million vehicles. So that's huge numbers. These are based on ASHTO that says ESAL per pass for each vehicle for cars is 0.0004. For pickup is 0.0001 ESAL. So the kind of numbers that we're coming up with are huge for life expectancy for cars and trucks. So we're not going to have this kind of traffic loading for a typical traffic loading. So I assume the medium traffic loading for my design purposes of 400,000 ESAL for pavement design that corresponds to 571 million uh, cars and trucks passing through the subdivision streets during the life expectancy of like 30 years. So we look at soil properties, and let's see if anybody's got a question. I haven't seen anything here. Okay, there's no question yet. We look at soil properties. We look at materials properties. We look at resilient modulus, reliability. For clay soils, for example, for design purposes, or the California bearing ratio is 5 to 15 for like clay soils. For sand and silts is 5 to 20. Subgrade modulus is 5 to 150 PCI. Is 100 to 300 for sand and silt. I assumed lime stabilized or lime fly stabilized subgrade. You will have a subgrade modulus of about 400 PCI, which is a good number. That's what AASHTO is using. We assumed the reliability of 75% for the data, and that's what AASHTO uses in their design for subdivision streets. We use a modular rupture of 1500 CBR. It's a property of the soil, and has to do with bouncing back when cars going on top of the soil. It's 1500 psi, and we use this design serviceability loss. This is the lowest index that you tolerated before rehabilitation is necessary. When the pavement goes bad, uh, this is the kind of a design serviceability loss that you have. You know, basically 0 means road is totally messed up and you can't drive on it. 5 is a perfect road. We use 2 for design, and standard deviation 0.35 I still use this for rigid pavement, which is concrete. And drainage coefficient identifies the level of drainage achieved under set of drainage condition. If you have fair drainage around your roadway, you can use CD of about 1.0. Load transfer coefficient. The concrete paving that we use for our subdivisions are what we call jointed pavements. For jointed pavements where they have control joints and expansion joints, J is 3.2. Modulus of rupture has to do with flexural strength of the concrete. And for a typical 3000 psi subdivision, is about 500 psi. Loss of support is used in design of rigid pavement to account for potential larger support from erosion in your lime stabilized or lime fly stabilization. For basically lime stabilized soil, loss of support ranges from 1 to 3.0. So this is the nomograph that AASHTO uses. So if you use a 400 PCI subgrade stabilized soils, again, your subgrade got to be properly compacted, and again, I'm going to talk about that, but you got to have proof rolling. You're going to have stabilization. Before you do any stabilization, you got to proof roll. Make sure you got to, and then you stabilize it. So you have effective modulus of subgrade of 400 PCI. You go to a concrete strength, elastic modulus, which is 5 million. You come over here, you go transfer here to mean coefficient of modulus of rupture. So it's about 500. You go to transfer line, you go here to load transfer coefficient, J of 3.2. You come to this line, and from here, you go to drainage coefficient of 1.0. Go to the match line. Go to the next page. This is your match line. And from here, go to design serviceability of 2.0. Go all the way down in here. And then you start from here, reliability of 75%. And standard deviation. Come all the way down in here. Then you go to traffic loading. We assume 400 million, 400,000 ESAL. Come to this line. You go all the way up here, you go all the way from there to here. It says you need 6-inch concrete paving. So that's the design pavement thickness of 6 inches. Go through all this approach and soil properties. So from an AASHTO standpoint, one way of calculating the pavement thickness based on the soil properties and stabilization, you need 6-inch paving. AASHTO also has this table for low volume roads for concrete pavements, and basically you go through this table here. You got a reliability of 75%. Load transfer device. Yes, we have dowels in our pavements, so we got a load transfer device, and then it says edge support. We don't have edge support. We don't have shoulders. No. I use the medium traffic loading for very good subgrade that assume your subgrade is compacted and stabilized. You need, basically for 600 the modular rupture, 6 inches of concrete, and for 700 modular rupture is 5.5 inches. So those are the kind of a table that it also provides for low volume, traffic loading. So it's got two approaches that Astro provides. So a typical subdivision streets, you go around the counties around. Harris County requires 6-inch concrete, 8-inch stabilized subgrade. Fort Bend is 6-inch, 8-inch stabilized subgrade. Galveston County, 6-inch concrete, 6-inch stabilized subgrade. Montgomery County, 6 and 8. Brazoria County is 8 inches and 8 inches of subgrade. Again, Brazoria County is pretty conservative. Liberty County is 6 and 8. Waller County, they really haven't defined what they are, but what we hear is 7-inch concrete and 10 inches of stabilized subgrade, which is a lot more than what's typically necessary out there. Again, Waller County's got that sandy soils. You need to lime fly ash it and use 6-inch concrete. Chambers County's got 7 inches and 6 inches. Again, this got to be 6 inches. Walker County is 6 and 8, which is good. I think the base, the stabilized depth was not really defined. It says by the geotechnical report. Grimes County is 8 and 8. So, again, Grimes County is pretty conservative, 8-inch concrete, 8 inches of stabilized subgrade. So if you're out there developing some of these counties like Grimes County, you're going to spend a lot of money on subdivision street concrete that eventually the homeowner is going to have to pay, and it's not necessary. This is a typical steel placement in some of these roadways for 3,000 psi concrete, 60,000 psi steel, and you got number 4 bars at 20.5 inches spacing for longitudinal steel. For transfer steel, number 4 bars, 36-inch spacing. So that's kind of a steel placement. It's a typical roadway. For typical roadway, we have control joints, 20-foot spacing along transverse, paving alignment, and along the longitudinal, 11, 12-foot spacing. Okay, that's kind of a control joints. It tells the concrete where to crack. So a typical Harris County, of course, precinct 1 and 3, you got expansion joints on your paving of 160 feet. Precinct 2 and 4, 80 feet. Transverse control joint spacing of 20 feet. Longitudinal 11 feet. Pavement thickness 6 inches. Stabilized subgrade of 8 inches. And a steel placement. Portland County, the pavement requirements. Basically, if in your pavements for subdivision streets, if you got out these bird bath here, if they're small, they're okay with it. But if you got big bird bath, you're gonna have to lift up your panel or remove it. That's not acceptable. That's not acceptable. It's not acceptable. Not acceptable. Not acceptable. They don't like water sitting in front of the driveways. They don't like water sitting here. You go out there and pour concrete in the water for your driveways. You need to take all the steel out and the forms and compact that area, dry it up, and pour concrete then. Big cracks within 10 feet of the expansion joints, removal and replacement of the pavements. Small cracks, okay. You can kind of fix them with epoxy glue. As long as they don't get bigger, they're acceptable. The cracks are the big cracks. If they're big and, they got vertical movements, they have to require panel replacement. Pavements out there near the manholes, if they don't compact the soils to 100% standard Proctor density around the manholes, they're going to settle and they're going to crack, and then they've got to be replaced. Compact to 100% standard Proctor density around the manholes. Dowel's got to be straight. don't have bent dowels. That's not acceptable. They develop cracks at the joints. So they're not acceptable. When you pour the concrete, you put curing compound on it right away. You got to put a lot of stuff in. It got to be totally white. This is not acceptable. You got to saw cut right away, usually 12 hours after you pour that concrete. You got to saw cut, put control joints in. You cannot put heavy traffic on the road as soon as you poured it. You want to get about 2100 psi before you pour before you can put any vehicle if you pour the concrete right away. Road construction. Back in the old days, Romans, were the inspectors. They build the roads, and if you cheated on your subgrade compaction and all that, they used the spears to get you straight. Here we just fail at the densities. First we do the clearing and grubbing, remove the trees and weeds and stuff like that. All the roots needs to come out. No roots more than half an inch should be there. All these roots need to come out. These areas you need to demuck them. Pump the water out, get the mud out, putting structural fill in it and compact an 8-inch lift and run density tests. Otherwise, you're going to have deflection in your pavements in these areas. All these areas got to be demucked. You got to pull all the roots out. Nothing more than half an inch got to be there. This is not acceptable. It's not acceptable. Look at that, all the roots out there in the pad. It's not acceptable. It's not acceptable. Not acceptable. They got a whole tree trunk in there. Got to get all the roots out. If you bring in fill, this is not acceptable. They cannot have all the organics in there. So they got to be good structural fill. Proof roll the area. That's one of the biggest things. You're going to get that subgrade proof roll because that's what I'm using, 400 PCI for my subgrade. Got to be stabilized, proof rolled and then stabilized, not stabilized then proof rolled. I had a contractor who wanted to stabilize before they're proof rolled. We don't accept that. We got to be proof rolling first, then stabilizing it. So you get a loaded dump truck, 25 to 50 ton. You go back and forth. This is the kind of like you see the deflection. Not acceptable. 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 Proof rolling is really big. It's really important. We cannot cut corners on it. You're doing a subdivision street, you got to have to proof roll it everywhere. You should have all this stuff in the test results. And the geotechnical, testing lab needs to have documentation of the proof roll. You compact that soil. If it's sandy, use a steel drum roller. If it's clay, use a sheep's foot roller. Run density tests. Make sure you got compaction. The way you run the density test, you poke a hole in the ground and you put your nuclear source in it. You nuclear source emits gamma ray. This radiation, you got detectors here. If a lot of radiation comes out of here, that means your soil is not compacted. If as little comes out, that means it's compacted. You compact your soils with sheep's foot, and then you go out there and seal it with a pneumatic so that if it rains, water doesn't get into your subgrade. That's a pneumatic roller here. Freshwater table, if you're out there in Katy, parts of the, out there on West Harris County out there, you got these sandy soils. Or you go out there, parts of Waller County, we have a lot of perch water in Waller County. You got these sandy soils over clay, that water just sits on top of the clay. Regular water table, 20 feet, perch water table, about 6 inches. You out there, remove the grass and weeds, and the soil turns into mush. You take the trees out. So water just sits in there, can't penetrate it. Here's a site that's pumping. That's in Katy. So contractor calls me and say, how am I going to build a road here? Is really concerned about it. So here are some of the ways you can try to improve that situation. If the subgrade is pumping, you can scarify and open it up, let it dry. You improve the drainage, you do soil mixing. You can do chemical stabilization, like you use lime or fly ash, and then a removal and replacement. Scarify, open it up. If you have a situation you don't have rain for a month, you can open it up and dry it up. Of course, that's not practical in Houston area. The soil gets rain on it, and it's a waste of time. So opening up doesn't work. Drainage, you can do your sites is pumping, do bleeder ditches, kind of drain the sand and silt. You put this in a grid, about 3, 4 foot wide and 3 foot deep. Drain the sand and silt. You take it to a detention pond, and then you pump it out, the water out neighbor's property. You can mix the sandy soils with clays. So if you got a site that you got sandy soils on the top and below it, you got clays in your detention pond or your channels, you take that clay that you got in your pond, you load it up, and you go out there and disc it into the sand, 60-40, 60% clay, 40% sand. You disc it in, get less than 1.5 inches in size, or you pulverize it like that. You can also do chemical stabilization. You can use fly ash or lime. This is fly ash right in here. You put fly ash on the sand, soil that's wet, and you go out there and mix it and compact it. That will dry it up. You can use quicklime. This is really good. Quicklime soaks that moisture out. You spread it out on the side and mix it. You can use dry hydrated lime. Do not use lime slurry. It's got already a lot of moisture in it. So removal and replacement with good soil. You can dig out all that sandy soils, haul it off the site, and bring in structural fill and put it in and compact it. It's not practical, too expensive. So if you can use bleeder ditches or do mixing, or use lime or fly stick for modification, I guess that's the best way to go. Make sure you run density test at 50-foot spacing. Chemical stabilization. Again, your subgrade is everything. If your soil basically is sandy, PI is less than 15, use lime, fly ash, or cement for stabilization. PI 15 to 35, you can use lime, fly ash, or cement. Above 35, we recommend lime. Lime stabilization, say it's not rocket science. You got to have to apply the right amount of lime, usually whatever it is, plus 1%. And because you waste some of it during the construction, control the mix depth. If your stabilization is 8 inches, don't mix to 10 inches. That's not acceptable. Use plenty of water. Use the top B lime, let it cure 72 hours. After the stabilization, you're going to have gradation. 85% past 1.75 inches, 60% past 0.75 inch sieves. Compact at optimum plus 3%. Scrape that soil. You bring in your lime slurry. You apply it in there. You mix it in. Add water if you need to. Let it hydrate. It will chemically change that soil through the hydration and change the texture of that soil after you pulverize it. You mix it in. That's the fat clay that you have in Arizona County. After you pulverize it with lime, you're going to get like this, the real sandy feeling to it. You go out there and run gradation of the sample of the soil after it's been stabilized. You bring the sample in, you run it through sieves. Of course, we got the gradation requirements that you have to have. And then you compact it with the sheep's foot. 95% is standard proctor density. The lime stabilized. Seal it with a pneumatic roller. Compact it with a sheep's foot. It's a lime stabilized subgrade. Run density test. In place depth check on the lime every 50 feet using phenol failing. Density test every 50 feet. Gradation every 50 feet. You apply the phenol failing every 50 feet. Watering counter is really big on this. You got to apply it on there, measure the depth. If it's supposed to be 8 inches and it's the stabilization to 10 inches, you reject it. Basically, you got the lime at the tip of 10 inch. It's supposed to be 8 inches. You're diluting the amount of lime. If your lime pH is less than 12.4, it's not going to be effective. So you reject it. That's how you measure the depth check. After lime stabilization, you got to pour that concrete right away. You put your steel in. Make sure these shrinkage cracks, these are bad. During the hot summertime, you're going to develop these shrinkage cracks that sucks the moisture out of your concrete. Then you develop shrinkage crack in your concrete. There's like reflective cracking. This is not acceptable. Subgrade. It's not acceptable. It's not acceptable. Lime fly stabilization. You go out there and apply type B lime. Basically fly ash type C or F, or you can do it in one mix. You got to compact it 2 hours. In lime stabilization, you let it sit for 72 hours to cure. Here, you got to have to go out there and add the mixture and all that compact it within six hours. You apply the lime, you pulverize it like that. Then you apply your fly ash. You mix it, add water to it, pulverize it, compact it with sheep's foot. Again, this is for sandy soils. You can also use cement. You compact it with the sheep's foot. Run density test at 50-foot spacing. Concrete testing, again, you cannot pour concrete if the temperature for 3 consecutive days, the temperature drops below 40 degrees. Normal concrete practice can be resumed once the ambient temperature above 50 degrees. If your concrete is cold, you pour it during the cold time temperatures. You get low strength gain with time. Void spaces in the concrete, corresponding to low strength. Reduced rate of cement hydration, corresponding to low strength, low durability of the concrete. So if the temperature is cold and freezing, you're going to have to protect that concrete until you get about 500 psi. Otherwise, your concrete is going to go bad. You put blankets, heaters, whatever you got to do to get that concrete, protected. Once you get to a 500 psi, which is usually about 24 to 48 hours, you can have one cycle of freezing and it's not going to damage your concrete. Hot weather concrete, your concrete should have temperatures somewhere between 75 to 100 degrees. If you pour the concrete when the temperature is hot, more than 100 degrees, and you're going to require increased water demand, accelerated slump loss, increased rate of setting, increased tendency for plastic cracking, difficulties in controlling in-train air, which we don't need in Houston, critical need for prompt early curing, decreased strength, decreased durability, non-uniform surface appearance, increased tendency for shrinkage. So concrete pavement construction, you stabilize your subgrade, you set your forms, put your steel in, make sure you got chairs underneath it, 6-inch concrete, expansion joints, you put them about 160 feet apart. You got your dowels, got to be straight. When you pour that concrete, you pour the concrete on the joint so that it covers both sides. Start finishing. You vibrate. Start finishing it. As soon as you poured it, you got to pour curing compound on it. Let it cure. You can use plastic sheeting on top of it. Seems like a lot of work. You got to go in there, put your control joints in. Again, control joints transfers about 20 feet and longitudinal about 12 feet. You saw cut 1/4 of the concrete thickness So if it's a 6-inch paving, you saw cut 1.5 inches. So you saw cut, put your joints in, longitudinal joints, transfer joints. Control the location width of appearance of expected cracks, accommodates normal slab movements, reduce stress buildup, provide load transfer when needed, maximize performance. So joints work. Here's the control joints out there, saw cut in the subdivision street. After it's poured, that's what they look like. These are the joints. You saw cut 1/4 of the pavement thickness and cracks below it. Expansion joints, these expansion joints, you gotta have to fill them with joint filler all the time, maintain them. You put them about 160 feet apart, otherwise grass will go through them and it starts pumping, and then you're gonna get pavement cracking around here. So it's important that you take care of your expansion joints. Slump test, your concrete slump should be 4 inches. Open counting allows 2 inches past the 4 inches. You can go up to about 6 inches. You put the concrete in this cone in 3 layers and 25 rods per layer. Pull up the cone. You measure the slump from here to here. It should not exceed 4 or 5 inches. If it's more than 5 inches, you reject it. Well, some counties allow up to 6 inches. Slump should not exceed 5 inches, but again, look at the specs for that county. This is 11-inch slump. You reject it. Too much water. This one here has got a like a 1-inch slump, not acceptable. What this says, he says, add 5 gallons to your concrete. You tell the driver, you add 5 yards. So for every yard of the for 1 gallon of water, add it to 1 yard of the concrete. 1 gallon of water to 1 yard of concrete. The slump increases by 1 inch. 1 gallon of water uses compressive strength by 250 psi. 1 gallon of water weighs 25 pounds of cement. 1 gallon of water increases the shrinkage by 10%. 1 gallon of water increases permeability by 50%. 1 gallon of water reduces freeze thaw by 20%. 1 gallon of water reduces salt scaling resistance. Increase cracking, increase air content, increase segregation. All the big stuff goes in the bottom. The fines go on the surface. Increases dusting, increases water damage due to traffic, increases finishing time. It's not worth it. Don't do it. Concrete temperature, again, we talked about temperature, 75 to 100 degrees, making concrete cylinders. You pour that concrete, you get a wheelbarrow, you pour the concrete in there, you put cylinders in there. These are 6-inch by 12-inch cylinders. You put concrete in 3 layers and rot it 25 times per layer. You smooth it out, put a cap on it, let it sit 24 to 48 hours on the job site. You cannot move them anymore. So otherwise you're gonna get low strength. You put it in a device like this, you take it to the lab, you put it in the curing room, 100% humidity, let it sit and test it at 7 days and 28 days. Now some developers use high strength concrete, early strength, so that they get their permit for housing. So they use, stronger than 3,000 psi concrete. That's the curing room. You test the concrete in here. You can see the strength here. At 7 days, you got these are high strength, 4,400, 4,300, 5,000 and 28 days, 5,100 psi. So the concrete's pretty strong here. You break the cylinder, it's concrete like that. Concrete cores, counties require you go out there, core that concrete to measure you got the proper thickness and strength. You go out there and core it, 1 core every 1,000 square yards. You core it like that. There's your steel in the middle. Cap it. Put a machine and break it. In general, concrete cylinders compressive strengths are 15% lower than the concrete cylinders compression due to curing conditions. So your core is going to be lower in strength than cylinders because cylinders cure in a curing room, in a controlled temperature, controlled humidity. These concrete cores are sitting in the cold or the heat, so their strength is going to be variable. ACI says if you're testing your concrete for concrete cores and concrete cylinders too, the strength should not, for any concrete core or concrete cylinder, should not drop below 75% of design strength. And not average of the three cores should not, should not be less than 85% design strength. Some of that has changed. I think right now it's two cores now. So if your design strength is 3,000, nothing should drop below 2250 psi. Nothing should average of three cores should not drop below 2550. Otherwise, your concrete strength fails. So in general, it's very important to do a proper geotechnical report on your project. If you don't, you're going to get pavement failure. That's a change order. So again, for some of these counties with 8-inch concrete paving or 10-inch stabilization depth, those are very conservative. What I suggest is, set up a meeting with this county engineer's office or the commissioners, and we go out there and do these presentations for them and tell them how we approach this from an engineering standpoint and try to educate them about how to do the pavement design. Got pictures of the pavements, failures or subdivision, send them to me. This presentation is going to be on YouTube, Geotech Engineering and Testing YouTube channel. We got a poll in here, so just want to kind of get feedback, see what you all think about this presentation. Maybe you can have some suggestion. You can email me the suggestions, and to make it better. My email is de@geotecheng.com. Phone number is 713-699-4000. We're going to have a bunch of webinars, so if you registered, you're going to get notices of those webinars. You're going to get 1 hour PDH. Any questions? Let's see if you got check questions here. Okay. Question here. What's the maximum depth of lime stabilization machine? Some of these machines, you can set it up, you can do stabilize 12-inch, 24 inches. Typically, we just do 8-inch at a time. The question here, is there a problem with water standing? Yeah, all that water needs to be removed. The air needs to proof rolled. If water is standing, you're not going to pass proof roll. So that's really important for you to be able to make sure you grade that. When you do mass grading, you got to make sure you get that grading such that if your water is there, it drains off. Okay, here's another question. Municipalities want developers to provide longer lasting streets. Their solution is often increased pavement thickness. What factors contribute to longer lasting streets? Obviously, when you go to 8-inch concrete, your pavement is going to last longer. But where typical pavements, like in Harris County, we have 6-inch concrete paving and they last 40, 50 years. And so, they perform fine. So you don't need more than 6-inch concrete. You don't need 8-inch. For CBR bearing ratio, the slide mentioned bearing capacity of crushed stone 100, but I think you said crushed limestone. Crushed stone or crushed limestone, they both are stone. Crushed limestone or crushed stone, they have CBRs very similar.